Today, I'm going to show you how to calculate simple specular highlights. Let's go! Last week, we started our series on custom lighting with vertex lighting, and I showed you a simple way to create diffuse and ambient light. If you haven't seen last week's video yet, I linked it down in the description so you can catch up. Today, we're going to pick up right where we left off from last week's video. We'll start out in Unity today, and then we'll switch over to Unreal in a minute. Before I show you how to create specular highlights, I want to show you something extra. An alternate method of calculating the diffuse lighting. What I'm going to show is called Half Lambert. It's a technique that was pioneered by Valve Software for the original Half-Life game back in 1998. And they've also used it in Half-Life 2 and Team Fortress 2. It's not a physically accurate way to compute diffuse light, but it's a more stylized technique that can give you more beautiful results in some cases. Remember last week when we talked about vertex interpolation and how it's causing these artifacts here right along the edge where the darkness turns into light? The reason that that's happening is because we have a very large change from dark to light in a very tight area here. Our shading goes from 0 to 1 in just half of the sphere. So the diffuse light is 0 on this half of the sphere and it's 1 on this half. So with Half Lambert, we take that gradient and spread it across the whole sphere instead, so the frequency of change is lower. So let's go ahead and add it in and see if it helps our artifacts. So right here we've got our dot product node, and this is what is calculating our lighting. So if we just wire this directly into our output color and save it, we're going to eliminate our ambient light here. Now all we have is the diffuse, and that kind of makes our artifacts stick out a little bit more. So in order to do Half Lambert, what we want to do is take the result of our dot product, which right now is going from -1 on this side of the sphere to +1 or white on this side of the sphere, and we're going to adjust that range. And the way we're going to do that is we're going to multiply by 0.5, and that's going to take our range from -0.5 to 0.5. And then we want to shift that range so there's no negative in it. We want to shift it into the 0 to 1 range. And so the way we're going to do that is by adding 0.5. And now you can even see what's happening in our little preview here. Our range has gone from, instead of -1 to 1, it's gone from 0 to 1 on the opposite side of the sphere. It's 0. So we've wrapped the shading all the way around the sphere instead of stopping with a hard edge here. So let's go ahead and plug it in and take a look at our result. So now you can see that on this side of the sphere, my lighting value is 1. And on the back side of the sphere, my lighting value is 0. So I've spread out the range of shading all the way around the sphere. And like I said before, this isn't physically accurate. Light doesn't actually wrap all the way around to the back side of objects like this. But it is kind of a stylized, and it can be in some cases, a more beautiful version of our lighting. So now that we have our Half Lambert, we no longer have those interpolation artifacts, and our lighting is a lot softer. So when you're building your own custom lighting model, this is a technique that you might consider using if you're going for a more stylized look, to adjust the range of your lighting here so that it wraps all the way around the model. Okay, let's create some specular highlights. I'm actually just going to get rid of our Half Lambert technique because we're not going to be using that for now. I want to start out by saying that the two techniques I'm going to show you today for calculating specular also are not the most physically accurate. In later videos in this series, I'll show you how to calculate much more realistic specular. What I'm going to show you today is basic and simple, and it's what you'd want to use if you want to make your specular as cheap and as fast as possible to calculate so that your models render as fast as they can. Or if you're trying to imitate a retro look. All right, so just a little bit of background here. When we calculate specular highlights, what we're actually doing is imitating the appearance of the light source reflected on the surface of the model. Specular highlights are a fake reflection. So with that in mind, let's create our first specular. So we're just going to move our graph up here. And like I said, we're creating fake reflections. And so I'm going to bring in this node called reflection. And what this does is it calculates a reflection vector. And in my case, what I want to do is calculate the reflection vector between the light direction. So we need our main light direction, and we're going to plug that in, and the normal. And so in this case, we're just going to use the normal vector. And so what I've calculated here is a reflection vector between the light and the normal. So my light is coming in, it hits the surface, and it reflects off. So the direction that it reflects off is what I've calculated here with the reflection vector. Now the next thing that I need to do is I need to do a dot product with that vector that I just calculated and the view direction. So I'll bring in my view direction here. And I want to make sure that these vectors are in world space. If you're doing math with vectors that are in different spaces, so like for example, if I were to put this one in object space and this one in world, the math would not be accurate. And so I'm doing a dot product between my reflection vector and my view direction. And now let's see what happens if I just wire this directly into my output result. I'm just going to connect this up directly to color, and we'll take a look at what we've got. Okay, so this looks kind of similar to the diffuse lighting that I was calculating before, but you can see that as I move around the specular highlight that I'm calculating, it's very large for one thing, and you can also see that it's kind of reacting to the direction that I'm looking at because of this dot product with the view direction. If I'm looking at it behind, it kind of spreads out and moves around the edge of the model. But if I'm looking at it from in front, it kind of shrinks to be right there in front. Now, as far as specular highlights go, this is a little bit too large. And so what I'm going to do to make this a bit more focused is add a power node. But before I do that, I need to go ahead and add a saturate node right here so that I can make sure that our values don't go outside the 0 to 1 range. So now, in order to make my specular highlight more focused, I'm going to add a power node. And obviously this value here, we can set to whatever we want it to be, depending on how glossy or rough our surface is. But in my case, just for now, I'm going to set it to a power of 8. And you can see now, if we compare our result here with our result here, raising this to a power, or multiplying by itself 8 times, has shrunk down our specular highlight and made it significantly more focused. So let's just go ahead and wire this out and see what kind of a change we get. Okay, now what we're seeing here is a specular highlight calculated in the vertex shader. And I warned you about this last week. I said we wouldn't be able to calculate specular highlights in the vertex shader, and what you can see here is exactly the reason why. Because we're trying to do something that has a very high frequency of change, it just gets ruined by the vertex interpolation. And so what I'm going to do at this point is just kind of say like, hey, I'm admitting defeat. We can't calculate specular in the vertex shader. I mean, we can, but it ends up looking like this, right? And so let's go ahead and make the change. So now our lighting is going to be taking place in the pixel shader instead. So in order to do that, what I want to do is come over here to my subgraph. And right now I have this color output. And instead of color, I'm going to rename that to diffuse. And I'm going to add a new output here. And we're going to call this one specular. And let's go ahead and wire our specular into that. And our diffuse into the diffuse output. And we'll save that. And now we'll come over here to our shader. And right here where our simple lighting is being passed into color, we're going to get rid of that. We're going to get rid of the interpolator here. So we're no longer doing that in the pixel shader. And then we're going to wire our diffuse into here where we're multiplying it by our texture. And let's just take a look at what we get from that. And this is what we were doing last week. Only now we're doing it in the pixel shader instead of the vertex shader. And then in order to get our specular in here, we're going to add our specular highlight on to the end. So just add our specular highlight and save it. And there we go. Now we have our specular here, and we have our diffuse lighting and our ambient lighting, and everything's combined together. And you can see that our specular is significantly more smooth. If we just wire our specular in so that's all we're seeing, now you can see our specular highlight looks really nice and smooth. And it's no longer exhibiting those really ugly looking vertex interpolation artifacts because we're computing it in the pixel shader instead of the vertex shader. Now, one thing that's cool about specular highlights, at least the way that I've calculated them here with the Phong model, is that as I look at the specular from behind, that specular spreads itself out and wraps around the edge of the model. So it's a really realistic looking look that I really enjoy. Okay, so let's jump back to our specular that we've calculated here. And I'm just going to draw a box around this. We'll group these nodes, and I'm going to call this Phong specular. And there are actually two different ways that we can control our specular. Right now we have a really glossy looking object, and we can control this, this effect in two ways. We can change the power, and we can also add a multiplier that allows us to change the brightness. So I'm just going to multiply this here. Let's multiply it by like 0.5, say, for example. And we can wire that in. And now you can see our specular is not quite as bright. So we have two controls here. This specular power controls the tightness. If we were to increase this to something like, let's try 16. Now you're going to see the higher our power value gets here, the smaller our specular highlight and the tighter and sharper that's going to be. And that represents a surface that's smoother. So the higher our power goes, the smoother our model is. And and we can also use this multiplier to control like how bright that specular highlight is. If we multiply it by something like 0.4, for example, that's the reflectance value of non-metallic surfaces. So if we're going for something that feels kind of plasticky, we might set our specular power to low and then set our multiplier to something like that. And then we've got a specular highlight. Now, these two control values, this power and this multiply, are something that we could potentially control with a texture. And we'll get into that in later videos where we start talking more about physically based lighting and how we can use like a smoothness map or a roughness map to control our specular highlight. But for now, what I wanted to show you was the formula for calculating Phong specular. So let's just go ahead and set this back to a power of 8 and wire this back in, and we'll go ahead and save it. All right, so there's our specular highlight. Now, I want to show you one other method of calculating specular, and this is one that approximates our reflection vector. So this node here that computes a reflection vector is a little bit expensive. And so if we want to do something that's even slightly cheaper than Phong specular, I'm gonna show you how to calculate Blinn specular. And this is just an alternate method that doesn't compute a reflection vector, but it approximates it. And so the way that I'm going to do this is I'm going to bring in my view vector. Actually, I'm going to bring in my view direction. So there's our view direction, and we're going to add the view direction to the main light direction. And in this case, I have to negate the main light direction to make sure that that vector is going in the correct direction for me. So I've got a dot product, or I've got my view direction added together with my main light direction, and then I'm going to normalize the result of that. And what I've just computed here with the view direction added to the light direction and then normalized is called a half angle. So I'm just going to add a little sticky note here, and we're going to call this the half angle. And this is the main distinguishing factor of Blinn specular versus Phong specular, in that in Blinn we calculate a half angle, which is kind of like an approximation of calculating the reflection vector. And now we're going to do a dot product between our half angle and our normal vector. So we'll bring in our normal vector and pass that into our dot product node. And now you can see in our preview here, we've got something that approximates a specular highlight, but again, it's very large. And so in order to control the size of this again, just like we did with Phong, we're going to add a power node and raise it to a power. Now, I don't know if you noticed, but in our power node preview, we have pink around the outside here, and that's because the values on the back side of the sphere are going negative. And so in order to prevent that, we need to add a saturate node here to make sure that the result of our dot product doesn't go negative. Like normally it goes to -1 around the back side, but when we add our saturate, it clamps it so it gets to 0 and then stays there. So now we can pass this into our power node. We no longer get that pink invalid data around the backside, and we can raise our specular highlight to a power to focus it. And now you can see we've got something that is similar to what we had with our Phong. So let's go ahead and wire this into our specular output and save it. And now we've computed a Blinn specular highlight. And one thing that's interesting about Blinn, you can see that I've raised it to a power of 32. And my result of a power of 32 there looks very similar to Phong at a power of 8. So here's my Phong at a power of 8. And here's my Blinn at a power of 32. So there's very different power values required for Blinn versus Phong. So that's something that you're going to have to keep in mind and be careful of if you decide that you want to make some models with Blinn and some models with Phong. Well, they're going to need very different values for raising to a power. The other thing that's different about Blinn is if I come around here and look at my specular from the back, it doesn't spread out anymore like the Phong does. So it's not quite as realistic at glancing angles. But it is just a little bit cheaper to compute the Blinn specular model because we're not wrapping or because we're not calculating that reflection vector there. It's just a little bit cheaper. All right, so I'm going to draw a box around this, and we're going to group these, and we're going to call this Blinn specular. All right, so we've got our Phong specular there. We've got our Blinn specular here, and I've showed you how to create two different specular lighting models. All right, let's go ahead and save that, switch back to our shader. You can see here we've got our simple lighting, which is that subgraph that we were working in. And coming out of our simple lighting, we have diffuse, we have specular, and if we add our specular and our diffuse together, you can see our complete shading model. Okay, there are some things missing here. We're not actually controlling our specular highlight with any texture data. And you can also see that it looks like our surface should be bumpy with the values that we're getting from our diffuse texture and also our ambient texture there. But we're not actually seeing those bumps calculated in the lighting at all. So next week, I'm going to show you how to use specular textures and also normal maps to improve this simple lighting that we've created. So we're going to go over using normal maps and specular smoothness, glossiness, and brightness maps so that we can control our specular highlights. So what do we got so far? We have our ambient lighting, we have our Lambert diffuse lighting, and we have our Blinn and Phong specular. And next week, I'll show you how to use normal maps and specular textures. So come back next week for that. And in the meantime, let's switch over to Unreal. Okay, here we are in Unreal, and we're picking up right where we left off last week. Here is the Lambert diffuse that we calculated, and the ambient lighting that has a top color, a middle color, and a bottom color. And here you can see we're adding our ambient lighting together, and we're using the vertex interpolator to calculate the ambient and the diffuse in the vertex shader. And then in our pixel shader, we're multiplying our textures by our lighting and passing it into emissive. And today we're going to do specular. But before we do specular, I wanted to show you how to calculate Half Lambert, which is the stylized Lambert lighting. So for now, let's just pass our Lambert lighting directly into our vertex interpolator, and then pass that directly into emissive. So all we're looking at is the vertex shading. And you can see that we're getting this linear interpolation artifacting right here on what's called the terminator, which is the edge between our light, the side of our model that's in light and the side that's facing away from the light. So these artifacts that we're seeing here are vertex interpolation artifacts. And we can use Half Lambert to reduce those and to create kind of a stylized look. Like I said in the Unity portion, Half Lambert is a technique that was made popular by Valve Software originally in Half-Life, and then in Half-Life 2 and also Team Fortress 2. So what we do with Half Lambert is for our diffuse lighting, instead of going from 1 at the lit portion to -1 at the in the opposite side of the model from the light, we're going to go from 1 to 0. So we're going to wrap that lighting gradient all the way around the whole sphere. And the way that we're going to do that is we're going to take the result of our dot product, a dot product of the normal vector and the light direction, and we're going to first multiply it by 0.5. And when we do that, instead of having a gradient value of 1 to -1, now our gradient goes from 0.5 to -0.5 because we've multiplied it by 0.5 here. And then to finish this off, all we have to do is add 0.5, and that shifts our gradient out of the negative range and now we have a gradient that goes from 0 to 1 instead of -1 to 1. So all we had to do is add a multiply and an add, and now we have a gradient that wraps all the way around our sphere. So here in the back, it's 0, and then here in the front, pointing toward the light, it's 1. And you can see that we no longer have those kind of ugly vertex interpolation errors that we were getting before. So this is one way of stylizing your lighting and getting rid of those vertex interpolation artifacts. Okay, I'm going to get rid of that for now because we're going to actually go with real diffuse lighting or real Lambert lighting and not half Lambert for the rest of what we do. But I wanted to show you that just so you could see what was possible. All right, well, let's go ahead and calculate our specular. And before we do that, what I wanted to tell you is that when we calculate specular, specular highlights are actually an imitation of what it looks like for the light source to be reflecting on the surface of the model. And so in order to achieve that, well, you'd think the first thing that we need to do is calculate a reflection. So I'm going to add this custom reflection vector node, and we need to calculate the reflection vector between our vertex normal and our light vector. So there's our vertex normal. We'll plug that into normal. And then we also need the sky atmosphere light direction. So this is the direction that our light is going, and we're going to take the reflection vector of our light source and the normal of our surface. All right, now the next thing that we need to do is negate this value. So I'm just going to multiply it by a -1 to flip it around so it's facing the right direction. And now that we've got that calculated, we can take the dot product between our reflection vector and our camera direction vector. So there's our camera direction vector, and we'll do a dot product between that and our light reflection vector. All right, we're going to saturate the result here so that we make sure that we don't get negative values. And then let's just plug this directly into our output and see what kind of results we get. So now you can see as we kind of come around here in the back, we've got this large blob kind of roughly in the direction of the light source. And as we come around the back, it kind of fans out and spreads around the edges of the model. And that looks pretty good, but for a specular highlight, it's probably too bright and too large. And so to control the size of it, what we're going to do is add a power node, and we're going to raise it to a power. And what this is doing is it's taking that value and multiplying it by itself as many times as I type in for a value, for our exponent value. So for now, I'm just going to use an exponent value of 8. And let's go ahead and pass this in to our vertex interpolator and see what we get. And what you're going to see here is that we're kind of getting a triangle soup. And it gets even worse if we raise this. So let's change it to a value of 16. Yeah. So what you're seeing now is that vertex interpolation error that we were getting before, just kind of subtly with our diffuse lighting, is now just kind of getting out of control. And it actually makes it so that we can see every single triangle on our sphere. So what we're going to do is we're going to go ahead and get rid of this vertex interpolator here and just calculate directly in the pixel shader, because it's no longer possible to get good results with something that has such a high frequency of change. It just doesn't work to calculate that in the vertex shader. So let's go ahead and take the specular highlights that we calculated here. And in fact, I'm going to go ahead and press the C key. Thanks for the comment in the in last week's video about that shortcut, by the way. That's super useful to just press C to create a comment. And I'm going to call this Phong Specular. Phong was the last name of the person that invented this specular formula. So now we can just plug this directly into our emissive color, and you can see we've no longer got those ugly vertex interpolator artifacts that we had before. Now our specular highlight is nice and smooth. Cool, because we're calculating it in the pixel shader. And you can see one nice thing about this method of calculating specular highlights is that as I kind of come around here behind the light source, this specular highlight spreads itself out so that it kind of goes around the edges of the model. That's really nice looking. All right, so that's how we calculate Phong specular. And if we take the result of, let's see here, we've got our diffuse here, and we've got our ambient here. We're going to multiply those by our textures and pass that in. And then we can just add our specular on top of that. So let's go ahead and we're going to move our textures down here just a little bit. Move this out here. And then we'll add our add right there. And now we're going to add our specular highlight to that. So now you can see we have our model with a nice specular highlight added to it. That looks pretty cool. I like that. All right, I want to show you an alternate method of computing specular that's slightly cheaper than Phong. Phong is just a little bit expensive, and by expensive, all of the techniques that I'm showing you today are super simple and dirt cheap using today's hardware. But way back in the day, when every single instruction was important and we couldn't waste anything at all, another specular technique was developed by Jim Blinn, and it's the Blinn specular technique. And instead of calculating this reflection vector, it does an approximation of this, so it's just slightly cheaper than Phong specular. So let me show you how to create Blinn specular highlights. So we're going to start out with our camera direction vector, and we're going to invert this, so we'll multiply it by -1. And now we're going to add it together with the light direction. So we'll do an add here. We'll grab this sky atmosphere light direction, copy it, and we'll add it together with our camera direction vector. And then we're going to normalize the result. And this normalized vector that we've created here by adding the camera direction and the light direction together is called a half angle. So we can take this half angle and do a dot product between that and our surface normal. So you can see here we're using all of the same components. We've got our camera direction vector, our light direction, our surface normal. We're just kind of rejiggering the way that they're combined. So here we do our dot product, and then we saturate the result of that to get rid of our negative results. And if we wire this into our output, what you're going to see is just like a very large specular highlight here. And we need to raise that to a power now. So I'm going to add a power node here on the end. And we'll just use an exponent for our power node of like 32. And now let's wire that out. Now we've got our nice specular highlight. So this is the formula here for calculating Blinn specular highlights. And I'm just going to hit C, and we'll call this Blinn specular. And back in the day, Blinn specular was more commonly used for metal surfaces, and Phong specular was more commonly used for plasticky surfaces. And Blinn is just slightly cheaper to calculate than Phong specular is. But what I wanted to show you is that so Blinn specular requires much higher power values, higher power exponents than Phong specular. So I think the equivalent here, if I set my power value for Phong to like 8, and we wire our Phong specular here, you can see that I've got a highlight that's about that size. Then if we wire our Blinn specular, so a power of 8 for Phong is pretty much equivalent to a power of 32 for Blinn. So their input requirements are just a little bit different. Well, let's go ahead and wire everything up here. We've got our Blinn specular added to our ambient and our diffuse, and we can wire that out. And now you can see we've got a nice, everything combined together. We've got our diffuse, our ambient, and our specular added right on the top. Well, there are a couple of things missing here. We don't have a normal map working yet, and we really need that in order to get everything shaped correctly. And we're not using any textures to control the sharpness or the brightness, the glossiness of our specular highlights. And that's the material that we're going to cover next week. So be sure to come back next week for that. And I hope you enjoyed today's video. You know, we covered Phong specular, Blinn specular, and I even threw in a little bit of a bonus of showing you how to do that Half Lambert diffuse lighting as well. So come back next week, and in the meantime, have a great week, everybody.